Hello, and thank you for attending my talk. I'm sorry I can't be there myself. I had intended to be there, but some family health matters came up, and I was not able to do that. So maybe next year I'll be able to attend in person. In any case, I'm going to talk about Zag Smalltalk. And Zag is a project that I've been working on for quite a while now, a couple of years. It's going slower than I'd like, but I thought I'd give an update on where things stand at the moment. So Zag is a brand new version of Smalltalk from first principles, and it's designed on the assumption that we have large memories today, that virtually all machines are 64-bit and have IEEE floating point. Multi-core is key to performance for a modern machine, and that we have relatively fast execution, but we want to relatively fast machines, but we want our Smalltalk system to actually run with good performance, because that has traditionally been an impediment for some applications. So it's from scratch implementation. The low-level runtime system is implemented in Zig, so it is not Smalltalk that gets translated to a low-level to C or some other low-level language. The low-level is actually implemented in Zig. However, there is no interpreter, so this is just this is the runtime environment, including garbage collector, etc., etc. The goal is to support existing open Smalltalk systems because I don't want to rewrite userland. And I'm not sure exactly when we'll get to the point where we could do that. Obviously, Quiz would be a good place to start because it's smaller, but it should ideally be able to work with Quiz, Pharaoh, or Squeak. So one way to speed things up is to move more things to immediate values. So Zag uses a whole series of immediate values. This creates less memory traffic. And so immediate values are all 64-bit, and I use a modified spur implementation. I'll describe a bit of detail about that. So this gives us double floats, 55-bit small integers, booleans, nil, Unicode, symbols, as well as some block closures, all in immediate values. Originally, I had intended to use NAND boxing, which you may or may not be familiar with. You can still, there is a compile time switch in the runtime that you can choose NAND boxing as an alternative, but the modified spur seems to be better for most purposes. So that's what most of the work these days is working on. So this is a graph of the immediate values. So nil is just a good old C null pointer. So all zeros is nil. Any 8-byte aligned object can be represented as a pointer. So you'll see the tag area. The bottom 3 bits are used like they are in Spur to encode the type, or the lowest level of the type. So 0 is a pointer, just as it is in Spur, the special case of nil being all zeros. Then we have the 001 in the last 3 bits, and this encodes a whole set of immediate values. So in Spur, that encoded just a small integer, and code 2 encodes characters. But I've included all of these in the 001, using the next 5 bits to capture other, or actually a class number. So true and false are there, for example, small integer, symbol, character, short strings, as well as a bunch of thunk values. And then floats are the range in Spur. Floats have the low 3 bits, 100. In modified Spur, I have used all the values from 2 up to 7. And that gives me a broader range of floating point values that can be recognized, and allows a fair bit faster conversion from tagged form to floating point. Yeah, so I'm not going to go through all the fine details here, but and here are some examples. So we have nil, native addresses, false is this. Here's an integer 2a, and this is how it's coded. So you can see it in there, and then there's the tag 61 at the bottom. This is the range of small integers. This is the smallest small integer you could encode, and this is the largest. In theory, I could use 56-bit small integers, but using 55-bit means that I can handle overflow a little bit more naturally, and so that's what I'm doing. Symbols, characters. I just came up with this idea of having short strings. So this is a immutable string that could be up to 7 characters long, and that can be encoded in an immediate value. Characters, I'm using Unicode graphemes is the character, and of course all graphemes cannot be fit in 48 bits, which is what I have available. So if a grapheme doesn't fit in that, then we code it as a character and use a memory object for it. The floats that have the asterisk beside them are ones that are encoded in SPIR, encodable in SPIR, and the other ones, the ones without the asterisk, are floating point values that Zag supports that SPIR doesn't. So this includes all the smallest values, the smallest possible values that you can represent. So basically anything with an absolute value less than or equal to this value, 2E154, are representable as immediate values. And then like SPIR, if it's a value that's larger than that, then the floating point value gets coded as an object in memory, including infinity and nans. So those values would be coded in memory. So we also have immediate thunks, and these are subclasses of block closure that are representable as immediate values. These are faster to recognize these, and it reduces pressure on the heap because we don't have to allocate heap objects. They're immediate instead. So there are 3 different categories. The first are non-local return values, non-local returns. So if you send one of these a value message, it will return something as a non-local return. So that means that if we go back here, the thunk heap, for example, has the top 48 bits as the address. In the non-local returns, these are all the address of the context that we're doing the non-local return from. So that gives us 8 bits. So we encode, so thunk return local, for example, does a non-local return from a context and returns the nth value, local value. So we can access up to 256 possible local values as what we're returning. Non-local return instance does the same thing, except returns one of 256 instance variables from the self object of the method. Small integer returns very small integers, plus or minus 127, basically, in that range. 8-bit integers, in other words. Return immediate returns only a very small number of the possible immediates, but it includes nil, true, and false. Return character returns, again, a very limited range of characters, basically ASCII characters. So any character that has that fits in 8 bits would be returned in a thunk return character. The reason for these truncated values is because most of the 64 bits is taken up with the address of the context that we're returning from. We also have block assigns, so we can assign local or assign instance variables. Again, in the case of block assign local, the address is the context, and block assign instance is so these are also non-local returns, but they return the value that you're assigning. And finally, we have other thunks. These are thunks that evaluate to a particular value, not return, so they're not return something. So we can have one that evaluates to heap object, any heap object, an instance variable, an immediate, or a float. The immediates include 48-bit integers plus all characters and so on, and the thunk floats include pretty much all the floats that can be encoded in an immediate, except that the bottom 8 bits have to be 0. So any floating point value that has the bottom 8 bit 0 can be encoded as a thunk that will return that value. To get faster performance in modern machines, machines aren't getting faster. Well, they're getting a little bit faster, but not very much. Mostly, we can do that by supporting multiple cores. And so Zag Smalltalk is being designed from the beginning with the intention of supporting multi-cores. So that means we're working really hard to minimize the blocking between cores. So the way this is structured is we have computational or mutator threads, and these typically we'd allocate one of these, so these would be processes in Smalltalk, and typically we'd allocate one per core. We also have I/O threads, or threads within the operating system sense, and one per open file. And so basically these will spend most of their time blocked on reading or writing to a device or to an object, and an operating system object. And then we have a global collector thread. So memory management, the mutator threads, each one, they use a copying collector. They have a private stack and 2 private nursery arenas. So it copies values back when values move off the stack or are allocated in the heap. They're typically allocated in the nursery arena and the current nursery arena, and then we use a copy collector to copy the live values from there to the other private nursery arena, and we copy back and forth. An object typically will stay in there as long as there is room, and then once there's no longer room, then we will promote objects that have been there the longest time into the permanent heap, into the global heap. So a mutator thread checks periodically to see if the global collector is asking it to mark, and when it is, it goes through a sequence of finding references to globals, and then it blocks. Then it waits for the collector a mutator to recognize those, and then it goes through and does the rest, and it keeps doing this until it's reported all of the refs or all the routes to the global heap, and then it proceeds. I/O threads just maintain a list of the current shared buffers while they're I/O blocked, and then we have the global collector thread. So the global collector is a non-moving mark and sweep arena. Non-moving because that makes life so much easier in a multi-threaded, multi-process environment. It periodically does a mark. It marks all the known structures, so the class table, symbol table, dispatch tables, and I/O thread buffers, and then it asks the mutators for the global routes, which I just described. Then it processes them until all the routes have been found, and proceeds to the sweep. So this is a very simple straightforward process. Obviously, there's complexities. It uses a binary heap for allocation, so it keeps track of all the objects of a particular size, and if it can't allocate something in the heap, in other words, if the largest size is not available, then it will ask the operating system for more heap space. So it grows the heap as appropriate to do that. Now you might say, well, a non-moving collector will eventually run out of space because it'll create holes that it won't be able to fill, and so we'll end up with a lot of fragmentation. The way we avoid that is that large objects, and large means probably at least a page size, so 4 kilobytes to 16 kilobytes, have separately mapped pages. So if an object, whether it's a simple object or an object with a variable component like an array, if that is all less than 4K, then it will be allocated in the heap, the heap proper. If it's larger than that, then the array portion will be allocated to a separately mapped page. So the header and the references and any instance variables will be in the heap itself, but the actual array portion will be in a separately allocated area. That area is not garbage collected. That area can be garbage collected if it includes pointer objects, but when the object becomes no longer reachable, then the separately allocated space will be freed up and given back to the operating system. So this means that we essentially cannot run out of address space because we have 256 terabyte of address space roughly, and so we'll be able to allocate spaces as necessary. This also means we can do mmaps of large files, which can speed up performance on those. Heap objects have a header that is 1 word long. It has a 12-bit length, which codes up to 4K. It has an age, which says whether the object is currently on the stack, in the nursery, or is global. And there's several different categories of global. The format is somewhat similar to Spur encoding, as in it codes various sized non-object arrays. But it also encodes pointer-free objects, so that those can be collected or not, or so they don't. If they're pointer-free, we don't have to scan them when we're collecting. Class index is the only hard limit in the system. Right now it is 16 bits, so it would collect, or it would support 32K classes, plus the corresponding meta classes. But if that was a problem, and in fact I am aware of some systems that have 100,000 classes, in that case we could move that boundary, so the identity hash would be a bit smaller, and we could increase the class index. Strings in the heap are stored in UTF-8 format. Okay. Another feature of how we gain performance is that we have a different dispatch model, and this is a single level of hashing for method dispatch. So each class dispatch table has an entry for every method that has been sent. So when you send a message to an instance of a class, if that method has not been called before, then we will put it into the dispatch table. And that is a somewhat expensive process. It has to go and find the method, either in the class itself or one of its superclasses. And then it compiles that method for that target class, and then it installs that in the dispatch table. There are many advantages to this, mostly having to do with inlining, but also to do with efficiency of the dispatch. So We also have a very good hashing algorithm using something called phi hashing, which if you're interested, you can talk to me. Some standard Spur OpenVM optimizations don't work well in multi-core environments. So for example, there is a global hash lookup that is done. That doesn't work very well in multi-core environments because updating it is expensive. So we don't use that. However, we do have polymorphic inline caches, but they're truncated somewhat. Because we have a very fast hash dispatch, we only use a relatively small polymorphic inline cache. So we don't use a megamorphic cache. And the exact size of that is something that we will tune over time, but currently we're using 3. And this is all somewhat similar to the JavaScript or self dispatch model. We also have very high performance inlining, so references to self and super are inlined, and this is possible because of the single level dispatch that we use. Methods also with small number of implementations, like if true, if false, for example, are inlined rather than heuristics. So there are no predefined selectors that we will inline automatically. Inlining happens only on the basis of can we figure out what the inlining should be. We also do tail call optimizations. This allows us to perform loops because if we do not recognize any automatic inlining, then we have to have a way to implement loops. Because in standard Smalltalk systems, while true and to do typically are inlined, and those are the ways that you actually get loops done, and everything else uses those. We don't support those as any kind of special thing. We just rewrite them so that they use tail call to implement the loops. And this allows us to inline many more looping methods than we would otherwise be able to do. Inlining prevents creation of many block closures, particularly non-local returns. This is just the way Smalltalk always is, but we're not doing this heuristically, we're doing this from principled inlining. It also provides larger compilation units for optimization, and we inline at the intermediate code level, so the threaded and the LLVM code are the same. And I haven't mentioned those yet. I'm going to mention them now. So there's no interpreter, but there are 2 code generation models. First of all, we have a threaded execution. This is similar to how Forth does things. And so a method is a sequence of Zig function addresses, and it uses threaded execution to thread through from one to the next, to the next, to the next. And this is reasonably fast. It's about a quarter the speed of Open Smalltalk VM, fully optimized. We also have a JIT. That's the other compilation model, code generation model. This is a work in progress. We're using LLVM to do the JITting for us because it has very good optimizations. But we're using only intra-function optimizations because our method call structure is not compatible with how we don't use native calls, for example. And this code generation model, we have seamless transitions. So we can initially a method will be compiled as threaded, possibly with very limited inlining. And then over time we will do more inlining, and then once it's fully inlined, we will switch over to a JITted version. But we retain the threaded version, and this allows us to seamlessly move back and forth between the JITted code and the threaded code. And the threaded code can be debugged, whereas the JITted code, we don't put breakpoints within the JITted code. So the breakpoints would be in the threaded code, but we can, as soon as you have some reason to go into a debugger, you can basically switch to threaded execution and stay there as long as that makes sense. So, conclusions. This is preliminary work. So there are a few remaining open questions, although most things are coming together. We have many experiments to run. This is based on a lot of my intuitions, but we really need to validate that intuition. And I would really appreciate pointers to real benchmarks. And hopefully I am now available on a Google Meet or some similar video conferencing process so that I can talk to you and answer any questions. Otherwise, feel free to email me, or I have my Twitter tag there, or X, I guess it's called, but I very rarely check it. So thank you very much for attending, and I hope this was interesting. If it intrigues you, by all means, follow up. I'd love to talk to you. Thank you very much.